All right, so this video is going to be talking about ionic compounds and specifically how to draw the Lewis structures for ionic compounds. Lewis structures are a way of representing bond formation that uses little dots to show the outer electrons. We're going to call those the valence electrons. Now remember that elements that are in this area, their outer electrons are in s orbitals, here in d, p, and f. We also saw that elements that were on this side of the periodic table tended to need to lose electrons to be like their noble gases. We called those givers, or things with low ionization energies. And as we moved over to the right, they tended to gain electrons to be like their noble gases. We called those takers. An ionic compound is when you combine a giver with a taker. There is a full transfer of electrons with an ionic compound. So I'm just going to go through and do four examples for you, and I'm going to derive each from its PES diagram. And here's what I mean. The first thing we're going to do is we're going to do a compound that involves Na with Cl. Okay, so I'm going to show you how to do this. So the first thing we're going to do is we're going to take Na, and we're going to do Na's PES diagram. So Na is going to make this the high side. So here we have 1s2, little break, 2s2, 2p6, little break, 3s1. So if you notice on the test, we showed that as the first break. There's the first energy level. Here's the second energy level. Here's the third energy level. That is the valence electron, or the outer electrons. The electrons in this outer, in this case, it's the third energy level. We call that n equals 3. Okay. Now let's go ahead and do that again for Cl. So Cl is going to be 1s2, 2s2. You don't have to do this. I'm just doing it to show you that they're separating into a new ring. 2p6, 1s2, 2s2, 2p6, 3s2, 3p5. Okay. Now again, here are the valence electrons. Those are the electrons in the outer energy level. Again, here that's n equals 3 as well. So here we have 1 valence electron, and here we have 5 valence electrons. Of course, this is binding energy. These electrons are the hardest to remove, and this is the relative number of electrons. So how would we represent this electron? Well, here's how you do it. You represent it like this, Na, and you put 1 dot up there. And how are you going to represent? Now, you know what? I'm going to erase this, and I'm going to do that dot in red. And here, this guy, Cl, and how many are here? Well, you have 2 and 5, so that's 7. And much like filling arrows in the paramagnetic diamagnetic thing, you can imagine we can have a total of 8 S2P8. So what we do is we spread out the first 4 like this. And then we add. And what I do is I circle the ones that are already paired up. So this one wants the bond, and this one needs a pair. So here, it's much easier to lose that and have your 8 back here, and here it's much easier to gain 1. So this is the giver, and this is the taker. So how would we show that? How do we denote this kind of bond? Well, what we do is something like this. We take, you know what I'm going to do? I'm going to do this one on a new page, but you don't need to do it on a new page. You can keep moving on from there. So this is going to now continue on to a new page for me. So here, what we would do is we would take Na, and we take Cl, 1, 1, 2, 3, 4, 5, 5, 6, 7. I'm going to circle these. Okay. And now we can see that this needs 1, and this has 1 to give. So there we're going to have the transfer of electrons. And I would like you to label this transfer in your notes. Okay. Now, when that happens, everything's been fully satisfied. So what we now have is we now have sodium with a 1 plus charge, and we have chlorine, who now owns all of the electrons. And here's how you're going to show that. You're going to put this in brackets like that. You have a 1 minus charge. And that is the balanced ionic compound. Okay, so this here is the ionic compound. And that's the finished product. And this right here, that's the ionic bond. Notice it's not necessarily a real bond. It's just, we're going to call it an ionic bond. Okay, well, let's do one that doesn't match up so easily. And let's go through the whole process that we did last time. So this time, let's do magnesium with fluorine. So the first thing we're going to do is we're going to do magnesium's PES, 1s2, 2s2, 2p6, 3s2. So we can see here that magnesium is going to have these 2 valence electrons, okay? The 2 electrons on the outer shell. So I'm going to put the first one like this and the second one like this. Fluorine, let's do its PS, 1s2, 2s2, 2p6, sorry, 1s2, 2s2, 2p5. So where are its valence electrons? They are right here. We have 2 here. Those are 2 valence electrons translated into those 2 dots right there, Lewis dots. And here we have 5. So we're going to translate those into 2, 3, 5. 7, I'm sorry. 2 and 5, 7. And I'm going to circle these, showing that they're already paired. Okay, so you might see here now, this one can take 1. It's got a slot for 1, but this one has 2 to give. So how are we going to do that in terms of a Lewis structure? Well, let's do it this way. So magnesium has 2, and fluorine has 7. 2, 3, 4, 5, 6, 7. Okay. So the first thing it's going to do is we are going to get a full transfer right there. Okay. But if we notice, that's already taken up. We have 1 more to give. Well, what's going to happen here is we need to bring in another fluorine. Okay. And now that empty slot here is going to give a place for that one. So when it's all said and done, what we're going to have here is a situation where the compound will look like this. Magnesium has now lost 2 electrons, so magnesium will be left with a 2 plus charge, and each fluorine has gained 1 electron. So it was a full transfer. Remember, this is a transfer of electrons, so it owns that. 2, 3, 5, 6. Okay. And there is your answer. This is the full ionic compound. And there's your ionic bond. Okay. So I know I said I would do 4, but let's just do 3. And here's what I'd like you to do. Right now, press pause. Okay, after I show you. So I'm going to have you guys do aluminum with oxygen all the way through. I'm gonna, in a sec, I'd like you to press pause, try it out, and then press play to see if you solved it. Go from the PES to the Lewis diagrams all the way to the Lewis structure. Press pause. All right, welcome back. Let's go ahead and see how you did. So we're gonna start off with aluminum's PES diagram. So 1s2, 2s2, 2p6, 3s2, 3p1. Okay, so I know I should have done that in red. Apologize about that. Stay consistent. So here are the valence electrons. There's 3 of them. 2 are in the s, and I'm sorry, this is 3p1. Should be down here. So 2 are in the s, and 1 is in the p. So that's 3, and those 3 are going to be represented like this. Okay. So that's a giver, because it would much rather lose 3 electrons to be like neon than gain 5 to be like argon. Now let's do oxygens. Oxygens 1s2, 2s2, 2p4 in that case. So here are oxygen's valence electrons, while here there was 3, here there's 2 and 4, that's 6. Now oxygen would much rather gain 2 to be like neon and then lose 6 to be like helium. So oxygen's a taker while aluminum's a giver. So it looks perfect, but we got a little bit of a complex situation here. Let's look at it. Oxygen here has 6 valence electrons. So aluminum has 3 to give, but oxygen has 2 to take. So you want to press pause if you only got to this point, try it and come back, or let's see if you got it right the first time. So let's go ahead and take a look. So here we go. Aluminum has 3, 1, 2, 3, and oxygen has 6. 1, 2, 3, 4, 5, 6. These are the valence electrons. They're coming from the outer electrons, the outer energy level electrons. Okay, so, ooh, that shouldn't have been circled there. Sorry about that. So this one is going to go there, and this one is going to go there. So the oxygen is satisfied, but the aluminum is definitely not satisfied. Okay, aluminum has still 1 to give. So let's go ahead and bring in another oxygen. 1, 2, 3, 4, 5, 6. Happy? Okay, so now this one has a place to go. But now the oxygen's not satisfied. So let's bring in another aluminum. 1, 2, 3. Okay, now the oxygen's happy, but the aluminum's not happy. So let's bring in another oxygen. Here we go. Let's do this. 1, 2, 3, 4, 5, 6. Oh my gosh, everybody's satisfied now. So let's go ahead and see what happened. Well, this oxygen lost 1, 2, 3 electrons. So it's got a 3 plus charge, that aluminum. And this aluminum here lost 1, 2, 3 electrons. So that's 3 plus, okay? And let's look at the oxygen. This oxygen gained 2 electrons. So this oxygen that now has 8 electrons, that's what we call its octet, has an overall 2 minus charge because it gained or took 2 electrons. Let's look at this other oxygen. This oxygen here gained 2 electrons. So it had its 6 valence, then it gained 2 more. I'm not circling them, but you can. So it's got a 2 minus charge. And now we still have our last oxygen. 1, 2, 3, 4, 5, 6, 7, 8. 2 minus. Perfect. And you see our new ionic compound now. This is now your ionic compound. Is a combination of 3 aluminum ions that transferred a total of 6 electrons to 2 aluminum ions that transferred a total of 6 electrons to 3 oxygen ions. And there's your ionic bond in there. and that is your final